go ahead and have a word of prayer. Dear Father in heaven, thank you for this day. Thank you that it's Friday, that we have a weekend to look forward to. Thank you for getting these students through another busy week. And thank you for the spring weather that we're starting to enjoy. Be with us now as we have class. Help the students to be able to understand this challenging topic and to be able to apply it and use it in their future. Thank you, pray in Jesus' name.
Amen. All right, so acid-base. And although it does have a reputation for being a little bit complex and tricky, I actually think that if we take our time as we go through it, it'll be very clear, very straightforward, simple, and importantly, very applicable to your clinical work. So let's go ahead and dive in here. At the beginning of this presentation, I've got listed off, I think, all of the major learning objectives that you're supposed to be able to understand by the end. And so I'm actually going to use this to guide my lecture to make sure I don't miss anything. And if you think I'm missing something that maybe I didn't explain, I want you to stop me and say, hey, number 4 says 3 forms of carbon dioxide. What does that mean exactly? Happy to cover it. We'll make sure we cover each of those pieces. Okay? So in that spirit, we're going to start with the very first one here, talking about what's an acid, what's a base in regard to their ability to accept or donate hydrogen ions. Okay. So simple enough. You're probably aware things like from your chemistry class, like HCl, hydrochloric acid, strong acid, and of course the reason it's a strong acid is we put that molecule into water, it dissolves apart, and there's a chloride ion, which we don't care that much about, but what we do care about is that it donates a hydrogen ion, and there you go. Acids all contribute hydrogen ions to solutions. Simple, right? Acids are essentially where there's solutions with lots of hydrogen ions within them. Okay. And then bases are just the exact opposite. A base is something that can take hydrogen ions or get rid of hydrogen ions. So like a very classic, if you had like a sodium hydroxide solution, if I throw that into water, I'm sure you guys all remember that turns into the sodium ion, okay, which we kind of just ignore. We don't care too much about it. But we do care about the hydroxide ion. That's negative there. And that hydroxide ion very much can bind with hydrogen ions and create water, and it gets rid of hydrogen ions. So bases essentially get rid of hydrogen ions, okay? Or can just turn them into something else. Okay, it's not always the same thing. It's not always water. It's sometimes just the molecule itself just adds the hydrogen ion to itself and just keeps it. But regardless, all of those bases will be taking hydrogen ions away. So, if you don't mind, I'm going to link that concept right immediately to number 3 here. We'll come back for number 2. And the reason I want to go to number 3 immediately is because I want to make sure this is really crystal clear. We got to always remember pH is exclusively measuring the concentration of hydrogen ions in a solution. So I like to draw stuff sometimes, so I'm going to draw on the little upper part of the screen. If I have, so I'm going to make little hydrogen ions here. If I have a solution that has a whole bunch of these hydrogen ions in there, and if I compare that to a solution that only has a few hydrogen ions, pH is sometimes confusing, but I want to make sure this is clear. pH of solutions that have lots of hydrogen ions, pHs there are low, right? Low numbers. So like this might be a pH, I'm just making stuff up, but if there's a lot of hydrogen ions in here, maybe there's a pH of, well, this would be non-biological, but a pH of 2 is a very low, pH. You couldn't live with a pH of 2. That's way too low, Biologically, if we were saying like someone's got a pH of like, low 7s, 7.0 or something. And then in contrast, solutions that have just a few hydrogen ions, it's going to have high pHs. Right? So it's going to be a higher number. So again, we'll just kind of make it oversimplified, but let's say someone had a pH of 8. Okay? And of course we use the terms acidic for solutions that are more on the, have lots of hydrogen ions, or basic. And actually alkaline is another term that we'll be using, especially medically. Sorry, they can't really read that there. Alkaline is what that says. Okay, questions? I'm sorry, yeah, I didn't see you there.
That's okay.
Yeah.
What did you say that pH is exclusively?
It exclusively measures the concentration of hydrogen ions.
Okay.
And of course, you have to calculate it using that log formula. Good news, not going to be asking you to calculate. Okay, we're just going to get pHs right off the medical strip, and it's going to tell us, here's the pH of the patient, good enough. We will have to do some other reasoning, though, using it. Yeah?
So like a low pH would be a high concentration?
Yeah, isn't that, it's counterintuitive. Yeah, in fact, I often will even draw that for myself. Have you guys ever seen this right here, where you've got concentration can be represented as like these little brackets? So that little thing there means concentration of hydrogen ions. And so I'll even do this just like, as soon as I would have a test in front of me, I would actually write myself across the top a little almost like cheat sheet so that my reasoning wouldn't go bad on me whenever I'm trying to reason through we will have to reason through like 4 or 5 steps sometimes with pH problems. I like to have it all written out so that I can go back to my steps and make sure I'm not misreasoning anyway. So what you just said is, if there's increased hydrogen ions, that actually equals a low pH. Right? And so I would actually write these sort of things down so that way when I went through the problem, they says, lots of hydrogen ions, I'd go back here, okay, yeah, right. It's going to have a lower pH, make sure I don't mess that up. And we're going to add to our little sort of cheat sheet sort of ideas. Other questions?
Concentration is same as molarity?
Concentration, one way of representing concentration is molarity.
Okay.
Molality is another one. Yes, those are all concentrations. Milligrams per deciliter, all kinds of ways to represent concentration. How many particles of something are in a certain volume? So it's kind of like mass per volume. Good. I think you guys asked some really good questions there. So we got number 1 done, I think, right? Differentiating acid and a base with regard to their ability to accept or donate. Done. Describe the relationship between hydrogen ion concentration and pH. Yep. Oh, and then now we got to note the normal pH of extracellular fluid. I bet you guys know this one based on just being around the clinic and everything else. What's our normal pH of extracellular fluid? You nailed it right there, 7.35. This is also one of those things that I'd want to make sure I knew, and then we'd be also on the top of my little cheat sheet thing. I'm not saying cheat. I'm saying when you have your test and you come in with just your brain, if you've got scratch paper or something else, you do that, right? You have scratch paper in your exam. Boom, you pull out your piece of scratch paper, and you just kind of lay out what you know in your head so that you don't make any mistakes of reasoning later on. That's what I'm saying. 7.35, 7.45. That would also go on my sheet. Okay. Does anyone know any sort of variance that we see normally? And this is a little bit of a side note. You're not going to have to memorize this, but it's going to help illustrate it. Why there's a variance, like some of our fluids are a little bit more acidic, some of our fluids are a little bit more basic, even in our own blood. You guys remember where this comes from? Or have you heard about that? Like venous blood versus arterial blood?
Oh, you mean just the oxygen?
So there's definitely oxygen in there, and bicarbonate and whatnot, but what's the real difference if we look at, well, you know what? I tell you what, let's answer this after I answer number 2, because number 2 will tell you. How about that? Okay, that's actually going to explain it. Differentiate between volatile and non-volatile fixed acids, including the sources of each. Okay, this isn't too bad. It sounds really odd, like volatile. Like, what in the world? Talking about like explosions or something? Think about the news. No. Volatile means that something can turn into a gas. And so there are some acids in your bloodstream that can turn into a gas. And the key volatile acid is carbon dioxide. Actually, that's technically not the acid. Excuse me. I probably need to write this out, but carbon dioxide can turn into carbonic acid. Does that make sense? So carbon dioxide can turn into carbonic acid, and that is the key volatile acid. And that's going to be, we're going to talk a ton about that CO2 down here on number 4. Carbonic acid. In fact, I can even draw it out for you. It is, so you of course know CO2, carbon dioxide, that can reversibly change into carbonic acid, H2CO3. H2CO3 is carbonic acid, if I want to capture that. That's the key volatile acid we're going to be encountering. Yep, that's the one you got to know. You'll see why we need to know that one as time goes on. Then the other one, the non-volatile or fixed acids, I think there might be a slide that'll have a nice little list here. So I'm going to go forward and see if I've got some. We've got our 7.35 or 7.45. We're going to talk about there. Yeah, here's what I was looking for. Fixed acids. Fixed acids, fixed acid means the exact same thing as non-volatile. If you see those, it's the same thing. Fixed and non-volatile means the same thing. And the main ones are sulfuric acid or phosphoric acid, and that's coming from breaking down amino acids or phospholipids. You normally metabolize some of those, and this is kind of like a byproduct. You know how you have like urea in the blood and all that, and you need to have the kidneys remove it? These are the same sort of things. A byproduct of normal metabolism, ends up in the bloodstream. Your kidneys do remove these as well, but they're in there they're in there too. And then there's also some other acids here too. Keto acids, what does that remind you of? Diabetes, like someone with a type 1 diabetes. Sometimes these will get produced whenever there's like high amounts of fat metabolism and your body's trying to compensate for not being able to get glucose into the cells. So keto acids. Lactic acid, of course, probably everyone knows that, byproduct whenever you got anaerobic metabolism going on in muscles especially. And then you can actually ingest certain acids like poisons that can you can actually drink literally things that will become acids in your blood. Ethylene glycol, also known as antifreeze. You probably heard of people killing, like you put a pan of antifreeze out and you can kill like raccoons and stuff with it. It's like, I'm not recommending that, but what's happening there is it tastes sweet, and that's why they're interested in actually trying to drink it. But as it gets into them, it gives them a powerful metabolic acidosis, which kills them. Okay, so don't drink antifreeze. That's the lesson for today, huh? All right. Okay. So those are the volatile and the fixed acids. I think that covers point number 2. Any questions?
One we need to know for non-volatile.
Be aware of, the ones that I would say you got to make sure you're aware of is you should know the sulfuric and phosphoric are normal ones. They're just byproducts of metabolism. You may need to know all 5 of these. I was trying to eliminate one of these, but you're going to have to know about the ketoacidosis, and that could come on and produce the same sort of a deal. Lactic acid. I don't know if I just go about memorizing all of these. The way that I keep it straight in my head is every kind of acid that I might ever encounter in the body, whether it comes from the body or not, is a fixed acid except for CO2. So like if I'm just trying to identify my fixed acids, if there's an acid that's in the problem is okay, patient's got this acid running around, it's a fixed acid unless it's CO2. CO2, then it's a volatile acid. So now we got to explain why that's volatile. CO2 and the carbonic acid, you can literally breathe that acid away. Every time you breathe, you're of course bringing in oxygen, but you're also getting rid of CO2. You probably have seen skin divers whenever they're going to go down and maybe spend 5 minutes under the water and try to hunt some fish with their spear guns. They'll hyperventilate, and maybe they're getting a slight bit more oxygen in their blood, but not that much. What they're really trying to do is get that CO2 out. Their body is actually more concerned about their acid-base balance and what's going to cause them to have strong feelings that they have to breathe while they're at the bottom of the ocean there looking up. It's actually they're breathing off acid. They're not trying to like get a whole bunch more oxygen, they'll be okay. No. They're actually they're breathing off that CO2, and with each CO2 molecule that they extra get out of their body, that's actually changing the pH of their blood. And then as they're under the water, of course their muscles and the rest of their body is producing constantly CO2 from metabolism, and that's raising the pH back to normal levels, and then eventually beyond normal levels. And then that's what's going to actually drive their brain, their breathing centers to be like, there's so much acid in the blood, you need to breathe. And that's what, that's why they're trying to do that. So volatile acid, CO2 is volatile, you can breathe acid off. That's one of the key concepts. Make sense? Questions? I love questions, by the way. Yes?
So for like people who like to do free diving,
Yep. Mm-hmm.
does that mean their pH, like they can
Yes.
stand a wider?
Potentially, I wouldn't say for sure, but absolutely, if they're able to resist the urge to breathe, then
Their body just gets used to the acid, obviously.
so either they're it's actually in your medulla oblongata in your brain, a little breathing center there. Either that's a little bit less sensitive to those acid levels, or they do a really, really good job of getting all of that CO2 out they possibly can, and all that acid, and they really pull their pH in the opposite direction, and then allows them to stay a little bit longer. Yeah, I don't know. I'd be actually curious to know the physiology of free divers or something like that. I don't know. Yeah, I just know this, a little bit. Okay, so I think we've done a really good job on those. And forgive me, I'm trying to be more disciplined. I used to just like rove around and just like talk about every topic in the world, but I'm going to be more disciplined. I'm going to make sure I would capture your learning objectives. And by the way, these learning objectives are both for today and on Monday. Is that correct?
Yeah.
Ellen, yes. So we've got time to kind of go through them and do what we're doing, a nice little deep dive. So done one. We've done number 2, differentiate volatile and non-volatile, including the sources. Describe the relationship between hydrogen ion concentration and pH and normal pH. Okay, so I was going to come back and talk about CO2 some more, and that's point number 4 here. We're asked to describe 3 forms of carbon dioxide transport and their contribution to acid-base balance. Now, I usually like lots of pictures, and so I'm praying that I've got a good picture coming up here, and I think I do. So I'm going to go ahead and show this. This shows the overall amount of carbon dioxide, and that's kind of cool. This is just an overview of let's remind ourselves of where's the carbon dioxide coming from. Your cells all of the time are producing CO2 as a byproduct of that metabolism. Essentially, I'll go more deep into that, but in your mitochondria, the electron transport chain, the whole 9 yards, CO2 is being produced, and it's usually about 200 mils per minute that's getting pumped into your blood by your cells. 200 mils per minute. That's actually a fair amount. Yeah. Now, it's, of course, not transported as a gas. It's transported in other ways. And then the goal is get it to the lungs. This is representative of the alveoli in the lungs, and the CO2 then is breathed off. Question? Oh, you can't see behind me. I'm sorry. I'm standing right in the middle there. I see, because I was pointing at the bottom there. I do like being wireless, so I'll wander around if you guys don't mind me doing that. That's just the overview. We were producing CO2. We got to get rid of it. Here are your 3 ways. They're all on this slide, and I'm going to circle them. Okay, here we go. Number 1, some of the CO2, but only a very small percent. I'll just give you an estimation. I don't know if this is quite on the right thing because it's been over a year since I've thought about it, but it's something like 2% or less is like dissolved as carbon dioxide purely within the fluid of the blood. Literally, it's just carbon dioxide hanging out in between water molecules just on its way, right? So you're probably aware that, gases do dissolve in blood, right? So Henry's law, if you may I had some traumatic memories there from chemistry, I don't know. Carbon dioxide, gases can dissolve in the fluid. Number 2, the carbon dioxide can also bind to, surprise, surprise, hemoglobin. So what this one is showing is that the CO2 will come along. It doesn't bind the hemoglobin in the exact same spot as the oxygen. I think, remember, the oxygen binds right in the middle of those hemoglobin where the iron is sitting in the hemoglobin molecules, and it binds there. It actually binds on you almost might describe it as more the outside of the hemoglobin next to some of the amino acids that are out there. Nonetheless, it can stick to the hemoglobin. And that carries a little bit more. I'm just going to give you estimations. Don't quote me on these. I'm sure you won't be tested on the percentages. Ellen's shaking her head no there. But it's maybe helpful to keep in mind. The reason I'm putting that down is because there's a third way. So that's way number 1, dissolved. Way number 2 is the hemoglobin. Number 3, carbon dioxide can undergo a change. Let me get it right here. Where's the best? I'm going to have to circle the whole thing. That kind of stinks. I'm going to go all the way like down here, I guess, just to get the whole enchilada. This is the main way. So if you just add those up, maybe if that's 88% there, huge amount is carried where carbon dioxide is transformed into carbonic acid, which will frequently just immediately dissociate into bicarbonate, that's the HCO3 minus, and the hydrogen ion. Yeah, no problem. In fact, I'm going to write this separately, if that makes sense, so we can see it really good. I'll come back to that slide, but I want to write it down so you can see. This is a formula that, there's no good white space. Maybe I'll go back 2 slides, if you don't mind. Yeah, here's a lot of white space right there. Here's the formula. This goes, we already got some things in our cheat sheet. This one's, boom. This is like the biggest thing that we're going to do today, and that is CO2 reversibly changes via an enzyme, carbonic anhydrase is the enzyme, into H2CO3, and that's carbonic acid, which immediately usually dissociates into hydrogen ion and HCO3 negative, also known as bicarbonate. Definitely have that written down and be able to know this thing right here. So what does this tell me? Okay, now on that previous slide we said the number 1 way that carbon dioxide is transported in the blood is it's transformed. It's CO2 for a second, but then there's an enzyme, carbonic anhydrase, that's that Ca I've written there, it's an enzyme. It facilitates the conversion of carbon dioxide. Ooh, I should write this over here. I apologize, guys. CO2 can't magically do that. CO2, there's some other elements in there, isn't there? CO2 plus, there's lots of water surrounding it. Does that make more sense now? It's a water molecule plus the carbon dioxide that transforms. So those two get combined into carbonic acid, which immediately dissociates. Here's the thing that I would really pull away from this. The more CO2 I have in my blood, the more hydrogen ions I have in my blood. Right? This is one of those, you see how I have those weird arrows, these little reversible arrows? You remember, what does that mean from your chemistry classes when you have those reversible arrows?
It goes either way.
It goes either way. It can go one way or the other. And do you remember some of the factors that can drive a reaction one way or another? Energy does it? Yeah, you can.
Stimulus.
Like an energy, lowering the energy of activation. What else? Catalyst. And actually, this is a catalyst. Cool enough. This carbonic anhydrase. This reaction, the one right there, doesn't happen unless that carbonic anhydrase is there. But do you guys remember? Does this make sense? If you add a whole bunch of one of the reagents on one side of an equilibrium reaction, it actually drives the reaction to make a bunch of whatever's on the other side of those arrows. Do you guys remember that? So like if I were to suddenly pour in a whole bunch of CO2 into this reaction, there's more CO2 molecules to react. And because there's more CO2 molecules to react, it's going to end up making more of the carbonic acid. And if there's suddenly more carbonic acid, it's going to end up pushing the reaction and making more of the hydrogen ions. Okay? So oversimplified version is simply this. More CO2, more hydrogen ions, which is more acid, which lowers my pH in my body. Okay, questions? if I'm going too fast or too slow.
You said it lowers the pH?
Yeah.
More hydrogen. Oh yeah, sorry, it makes it more acid.
That's right there. Did you guys hear this? That's why I write it on my test, right there. Because it's easy to do. It's like, it's reversed. You write it and you don't make the mistake. You double check yourself and say, okay, does that actually, because it's those little mistakes that you could know the whole concept and that little mistake, I lost the whole question, the whole point because I made a simple conversion. I did the opposite. And guarantee in these questions, Ellen will have the opposite as the answer as well as an option, and that'll get you. That'll get you. Look at her. She's evil. No, she's not evil. No. All tests are that way, including your board exams. As you guys take those, they'll be having those options as well. Not just Ellen. They're trying to get you tough so that you're ready for the long haul there. Okay. Other questions? Does that make sense? Yes. Yeah, go ahead. You go first.
Is HCO3 acid or base?
Yeah, this is actually a base. The HCO3 is actually a base bicarbonate. You want to play with this equation? This is actually kind of fun. Here, let's play with the equation. Let's go back here, and I'm going to take off my little arrow off the hydrogen ion if I can without deleting everything. Okay. Okay, so the question up here was, is the HCO3 a base? And it absolutely is. This is bicarbonate. You guys know you can give bicarbonate, of course, in the clinic. What happens if I have a patient and I suddenly, into their bloodstream, I give them a whole bunch more bicarbonate? What happens? You're taking away the hydrogen ions, and the reaction's getting pushed this way, right? So yes, you actually make them more basic. So like a patient that already has like a ton of acid in their blood, you give them bicarbonate, it's going to get rid of that acid. Mm-hmm. And as long as their breathing is normal, they'll actually just breathe that CO2 off. Hey, no big deal. Okay, questions? Yeah.
Okay, so like, I know you're not a clinical professor.
That's okay.
So
I'll
maybe
try.
I might say this
Ellen,
one to you.
yes.
But like in like a clinical practice setting, like I know a couple weeks ago we had a code in clinical. And so would I remember that they gave like a ton of bicarbonate. So would they give that because the patient was not breathing on their own? So that's why they would be giving that would be to reverse this acidic state.
Well, I think Frankie can answer this, but in absence of oxygen, what kind of metabolism does your body do?
So they've got lots of what kind of acid floating around? Yep. Which lactic acid still gives hydrogen ions, right? If we actually look at the molecule of lactic acid, all those acids, all of them, are just throwing hydrogen ions into the blood. So that patient had a lot of hydrogen ions in their blood. And so then, yep.
Plus, but you're right, they're not breathing off CO2.
Right. And even if you drive the reaction this way and they have a lot of CO2, the CO2 itself is not going to hurt them. Does that make sense? It's just a gas. It's when it's in the acid form, that's what's going to get them. So you just drive the reaction away from all those those hydrogen ions. Okay. Other questions? Okay, that's a super helpful formula, and we're going to use this formula all the time when we try to solve the problems for this area.
So when
Yes.
we have, like you were saying, like when we have more carbon dioxide.
Yeah,
like,
more carbon dioxide, yep.
We will have more acid,
Yep.
hydrogen ions.
Yes.
But will we also have more HCO3,
Yes.
but it won't make it become base.
It won't make... Oh, yeah, it eventually could. If you gave someone too much bicarbonate, you're saying like... Oh, I know what you're saying. This is a tricky concept. Oh, great question. She's saying... Oh, hold on a second. This doesn't make a lot of sense. For each carbon dioxide molecule, I do get a hydrogen ion, but I also get a base. So doesn't it all cancel out? Doesn't it just end up being, it all averages out in the end? No, it doesn't. Why? pH is exclusively the measurement of free hydrogen ions. We don't care that there's one of these hanging out unless this one binds with it and takes it away. When people are dying because they have too low a pH or too high a pH, only thing that matters is what is the concentration of these guys. You might say, that's not fair. I mean, these guys have a vote too and everything. I know that's not fair, but literally, it's all about this. And the biology centers on it as well. Okay? All the biology is around how many hydrogen ions do we have floating around. Yeah. Yes, question, yeah.
Sorry, just to summarize the three forms of transport, is the first one is it dissolves?
Yep,
The second one is it binds to hemoglobin?
yep.
And the third one is this whole undergoes a change.
Yeah, it turns into carbonic acid and then bicarbonate. And actually, it's in bicarbonate. The CO2 part of it is actually in this bicarbonate form for most of its journey. So often it'll be, the problems will, or just in general, people will say the CO2 is transported as bicarbonate. Does that make sense? Because it's literally kind of like, if you were to look into that molecule, there's a CO2 in there, and it's transported there. Yeah. Questions? Anything else? Yeah.
So when CO2 bind to hemoglobin, oxygen cannot bind to hemoglobin.
You know, they actually, ironically, yes and no. They kind of can, but they work against each other. They don't bind in the same spot, so they don't compete for the same active site. But funny enough, whenever CO2 starts to bind hemoglobin, it makes hemoglobin change its shape ever so slightly, which means that when it changes its shape, it'll make it easier to pop oxygens off. And it actually does that intentionally. I'll go back to, do you remember this slide here? You know, when the capillaries were not only getting CO2 from the cells, but of course oxygen's going to the cells. And so you can imagine, whenever you get near the cells, there's lots of CO2. And so that CO2 begins to kind of bind with the hemoglobin, which makes the hemoglobin throw off oxygens, which is the right time to do that because the cells need the oxygen. So it's a very synergistic, they work in opposites of each other. But it's not 100%. You could find a hemoglobin molecule that could have some oxygen on it and some CO2 on it, but they don't really like each other. They want to force each other off. Yeah. And the opposite happens in the lungs. The oxygen helps force the carbon dioxide off in the lungs. Okay, that's just a little good side note there. Good questions. Let me go back to our plan. Be very disciplined here instead of just wandering off into the weeds. Okay, so we've done our three forms of carbon dioxide transport and their contribution to acid-base balance. Their contribution is, beware, if the CO2 is dissolved, has no effect on acid-base, right? There's no hydrogen ions. We know that the hydrogen ions is all that matters for acid-base. So dissolved CO2 doesn't affect it. The CO2 that's bound to the hemoglobin doesn't affect it. Again, there's no hydrogen ion change. Of course, the one that makes the bicarbonate and the hydrogen ion, that affects pH very much so.
Can you repeat that?
Sure. In the three forms of carbon dioxide transport, only the form in which it's transported as bicarbonate, and of course it is then producing an extra hydrogen ion, that form affects the pH of the blood.
That's just because that conversion causes that addition.
Yep, you got it. Yeah, you get an extra hydrogen ion there. Whenever every CO2 molecule that converts, you get an extra hydrogen ion molecule. Okay, well, let's identify next the three major mechanisms of pH regulation. Yes, question? Sorry.
Sorry, I just,
No,
okay, so
no,
the
Ed.
contribution is if CO2 is dissolved, it doesn't affect
It doesn't.
acid base.
It doesn't affect acid-base balance. Whenever CO2 is just dissolved in the fluid, it doesn't change it.
So is that all I have to know for contribution, or did you say something?
Oh, I'm sorry. Yeah, and so the CO2 when it's dissolved, that doesn't change it, and neither does when the CO2 binds to hemoglobin, that doesn't change it. So that's two of the three. But then the third one that we talked about, the last one, where it's transported as bicarb, that one definitely affects the pH. Yeah. Good stuff. I tell you, this is fun stuff. I mean, people make a big deal. Oh, acid base is terrible. No. It's good. It's very good. One of my highlights of my semester is coming over to hang out with you guys. You know? Does that say how bad my job is? Wow, he's excited about acid base. That must mean his rest of his job must be terrible. No. All right. Okay, so identify three major mechanisms in pH regulation. Okay, so pH regulation. I need to make a quick point before we go there that's kind of even more foundational point. You guys already know this. pH has to stay between 7.35 and 7.45 in the body. Why? Why? Who cares?
Gastric functioning, right?
Okay, well, so some systems in the body, like the stomach, has a lot of acid in it, and you have to have those systems rely upon having certain pHs on the other side, like in the extracellular fluid. That's partly why. But what happens to your patient, like this patient that's coding? Let's say their pH is way off. What's going on in there? Like organ failure and all that? Here's what's happening that underlies all of those terrible things. Do you remember that proteins, whenever they fold themselves up, that it's the structure of the protein that gives the protein its function, right? So like an enzyme has a certain three-dimensional structure. It might look like a pair of scissors, and that allows it to cut things, right? That three-dimensional structure is highly dependent on the pH. And it'll actually, you start to mess with pH very much, the proteins will all suddenly change their shape. Well, when they change their shape, they stop doing their jobs. Your enzymes stop doing their jobs. Oh my goodness. You can't process your glucose. You can't make all of the molecules and hormones that you normally need to make. Every biological function in your body begins to fall apart because the proteins are all misshapen and they can't do their jobs. So your body is going to be like, okay, we're keeping the pH in a really narrow range. 7.35, 7.45, that's it. Okay. All right. So any questions on that? Does that make sense? Okay. And I don't think you're going to get tested on that one. I don't think it was a learning objective, but for me, it's helpful. Like, I want to know why. Like, what fundamentally is going on deep that makes it so that we have to maintain that pH. So you need to know 3 ways that your body maintains that pH. 3 control mechanisms. One of those control mechanisms is right here, and that is, you guys in chemistry probably covered buffers. And buffers are important things in that they are chemicals that reduce the change of pH. So the pH doesn't move as much in response to changing the amounts of the hydrogen ion in the solution. It reduces the amount that the change occurs. So like, for example, these are fancy graphs here that are showing the titration curves of some weak acids. The 2 weak acids they're showing there is, do you notice, look at this, they're showing CO2 on this end, and then if I go down here and I point, I have HCO3. It turns out that the reaction that we drew earlier that showed bicarbonate on one end and then carbon dioxide on the other end, that is a weak acid. In fact, specifically right here in the middle would be H2CO3, if that makes sense. And what they're showing is, when you try to change the pH on a solution that has that molecule in it, it actually takes a lot of addition or subtraction of hydrogen ions to actually move the pH. Do you see how steep the line is from like here through here? If this was water, this line would be like horizontal. And what I mean is, if I added just a little bit more, or not horizontal, it'd be like more like a straight linear line, like on a line like that or something. Okay. But what this graph shows is, and you don't memorize your graph, just memorize this point. I can either add a bunch of hydrogen ion or take away a whole bunch of hydrogen ion, and the pH barely changes. Let me make it even more clear. I had a cool little experiment here that I had. I saw that slide. I think I skipped over it. The Pitts experiment. I think it's back this way with the dog. Right here. It's terrible. Probably unethical. In fact, it is unethical probably today. But over 100 years ago, there was a researcher. I think his name was William Pitt. And what he did was this. He took a certain amount, 150 milliequivalents of hydrogen ion, And he literally injected that into a dog. No joke. And then he did the exact same amount into about 11.4 liters, which he estimated being the same amount of fluid as what's in the dog. Okay? And then he measured the pHs. And the water had been at 7, and the dog had been at 7.4 or whatever. And then he measured the pHs afterwards. And what happened? The pH of the water was 1.84. Really low. The pH of the dog, 7.1. Now, still low biologically, but he put the exact same amount of hydrogen ions in the dog as he did in the water, and the dog's pH barely budged. That's because of the buffer. The buffer is resisting change. It says, no, 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 you can try to put a bunch of hydrogen ions in there. We're keeping the pH the same. Questions? Does that make sense? Dog was okay. I think the dog survived. Yes, it did. We'll maybe use the dog as examples later on. Like what happened in the dog immediately as soon as that occurred, and later on we'll actually talk about how does your body compensate when there's more acid? What can you do? And we'll point those things out. Okay, so that's number one in our 3 mechanisms was the buffers. Buffers resist change, and that helps control the pH. Number 2, be aware in your kidneys. Now, this slide may not make sense initially, but do you remember in your kidneys you've got the nephrons? And each of those nephrons are specialized to filter your blood. And in the tubule part of the nephron, there's fluid in there that came from the blood, and that fluid is being basically your kidney nephron is trying to keep things in that fluid that it wants to get rid of, and then reabsorb back into your bloodstream the things it wants to keep, if that makes sense, like the glucose and many of the ions and all that stuff are reabsorbed. Well, your kidneys can actually change your pH because they can produce bicarbonate in order to help get rid of basically acid. So look on this slide here. There's a cell in the kidney. That's what this whole structure here in the middle is. And it's quite literally, it's got water, it's got CO2 in there, and look what it does with it. It forms the carbonic acid, the same thing we've been looking at. The carbonic acid dissociates. The acid gets pumped into the tubular lumen. That's eventually going to be turned into pee, right? That's going to be urine, right? And so that's going to leave the body. But then it's going to keep a bicarbonate. And now we do care about this bicarbonate because that bicarbonate's in the interstitial fluid. That can go back into the blood, and extra bicarbonate can bind with hydrogen ions and reduce the number of hydrogen ions. Yeah. Does that make sense? So your kidneys can change your pH. Yeah.
Is the bicarbonate acting as a buffer, or what makes that process?
Yeah. The bicarbonate, as it goes in there, will act as a buffer. If it bumps into a hydrogen ion, it potentially can recombine with it, form carbonic acid, and then form the carbon dioxide.
So there's 2 different things going on there.
Yes.
You're excreting more through that process.
Yep.
You're excreting more hydrogen ions into urine.
Yep.
But you also are putting more bicarb
Yep.
back into the blood, which can then bind with the hydrogen ions.
That's right.
So you've got,
It's a double process here. Yeah, that's right. The net gain, though, is your kidneys can make new bicarb. And here's the cool part. They can actually control how much they make. So your kidney's just not hanging out there just making a constant amount. Your kidney is actually measuring your pH. And if the kidney goes, holy mackerel, the pH is very low, or in other words, there's tons of hydrogen ions floating around this person's bloodstream, I'm going to start making a bunch of bicarb so that that bicarb can recombine with those hydrogen ions and help get that pH back to a more normal range. Not sure if it has that kind of self-talk, but I know the process is happening.
So they don't need to send a message to the brain?
No, it's local pH detectors. There's little local mechanisms that actually can detect the pH on the local site that help it run. Yeah.
I'm sorry, I have a question about the last one.
That's okay. They'll be on these.
The buffers?
The buffers, yeah.
So,
Where did the buffers come from? Like what?
Yeah, I should have said that. So here's a couple of buffers that are in your bloodstream. The most important buffer is actually the bicarbonate, carbonic acid, carbon dioxide buffer. And you guys know where that comes from. It comes from the carbon dioxide that's coming off of your cells. You gotta admit, that's pretty cool in that here's a waste product, CO2, but look at the dual usage of it. It actually ends up working to help maintain the pH at the same time. So it's not just like a passive metabolic byproduct that we just need to get out of the body. The body makes good use of it. The body's got a sweet little enzyme that can help convert it into this bicarbonate form, and that helps keep the pH in a very narrow range.
So the buffer is a process? Is the buffer a process or like the physical?
Yeah. So when you say a buffer is, you can refer to the specific molecule that is the buffers, but the reason it's called the buffer is because it's a molecule capable of accepting weakly binding hydrogen ions and thereby making it so the pH does not change very much whenever we change the concentration of hydrogen ions. Yeah.
So then in our bodies, the buffer that is used a lot is the one that takes away the CO2.
Yes.
And so it's that right there. Right?
That's right.
Other ones.
There are other ones. There are other ones. For example, this H2PO4 right here, this is phosphoric acid. It's also a buffer. That's also actually a metabolic byproduct. It also helps buffer. Did that answer your question too?
Yeah.
Think you're good on that one? Okay. Well, I think that's about a good maybe time to break. We've gone through our mechanisms. We have more control mechanisms. First control, we had buffers, we have kidneys. When we come back on Monday, we'll do the mystery number 3. What's that one? Okay? I have to leave you a cliffhanger right there. All right. Have a wonderful weekend, you guys. I look forward to seeing you on Monday. Monday.
It'll be after an exam.
Oh, no. Exam.